Hi, everybody. Oh, that's in my face. OK. My name's Paul. I work at RISC Zero, and I'm excited to talk to you today about the sort of architecture of our proving system at RISC Zero, which happens to be very, very similar to the sort of proof system architecture across a number of other kind of mature zkVM systems. So if you look at the details of the RISC Zero architecture, the Polygon zkEVM architecture, and the zk-sync's new Boojum architecture, all of them have really quite a similar pattern. And I just sort of wanted today unpack what does that pattern look like and what are some of the kind of considerations that drive the choice of that pattern and drive the conversation about whether we might want to pivot away from that pattern at some point in the future. So, brief overview, we're going to talk about what is this emergent pattern and what metrics are relevant in considering alternatives to this pattern. So I think probably the people in this room are relatively aware of zkVMs, so I'm going to sort of like speed through this relatively quickly. But general purpose zero-knowledge virtual machines are here, and we think they're going to continue to be quite important moving forward. So let me just unpack what I mean by a zkVM. I'll make it quick. In a typical virtual machine, you feed in some program, and you feed in some inputs to that program, and you get out some output. In a zero-knowledge virtual machine, you have a very similar setup. You feed in some program, you feed in some inputs, you get out some output. But in addition, you get out a proof that the output actually corresponds to the program and the inputs that you specified. At RISC Zero, we package this output and proof into one object that we call a receipt. And at this point, we can sort of get into the main question of like, OK, yeah, we want to make proofs for zkVM executions. How should we make these proofs? Should we use FRI? Should we use Groth16? Should we use some sort of folding-based approach? Should we use some sort of lasso-based approach? And what we see right now across these platforms that I'm discussing today is a pattern that looks something like this. So we're going to unpack this picture quite a bit as we go, but I just wanted to give you a brief sort of preview of the architecture here. So these orange objects here are receipts, and this is like the stack for a single proof of a RISC-V execution. So we generate a bunch of receipts, and then we use recursion to compress those into a single receipt. And then finally at the end, RISC Zero is using a Groth16 circuit to compress this into something small enough for on-chain verification. The other two platforms, or Polygon and zk-sync, are both using KZG for this. So we'll dive into this in quite a bit more detail as we go. But you can see here there's a few kind of layers of proving here. Initially, we run provers to generate these 6 receipts shown here. And we're using FRI for those proofs. And then we do recursion, and we're using FRI for those proofs also. And then finally, we wrap it up to make it small. And this is, in our case, Groth16, in the other platforms, KZG. So let's talk a little bit more about recursive proving, because there's kind of 2 separate applications of recursive proving that are relevant in this stack. And I want to kind of decouple them a little bit so we can consider whether we want to use the same proof system for both of these kind of contexts. So the basic motivation for recursive proving is to take a bunch of proofs and compress them into a single proof. So I have a picture here. We have 4 receipts, 4 proofs. We feed 2 of them. We feed pairs of them into a recursion circuit, and they each spit out a single proof. And we feed those into another recursion circuit, and they spit out another proof. So we can use recursion to compress a bunch of proofs into a single proof. I want to call out here that there's these initial receipts here. I'm imagining they came from the zero-knowledge virtual machine. They came from a RISC-V execution. And there's actually 2 SNARK circuits in this picture here. There's the initial RISC-V circuit, which is used to generate our proofs of RISC-V execution. And then there's a separate recursion circuit, which is used to compress those. And I want to just call this out in order to sort of invite the question of, it might be that we want to use a different proof system for the RISC-V execution from the recursion. Right now, we are using a SNARK-based system for both of these. But I think it's important to call out that it might be the case that there's a reason to stick with FRI for one of these, but switch away from FRI for another. So let's talk a little bit more about recursion. We just discussed one purpose of recursion, which is to aggregate a bunch of proofs. But at RISC Zero, we're also using recursion as a mechanism for incrementally verifiable computation. So I'm not going to unpack what I mean by incrementally verifiable computation. I apologize if you're not familiar with the term. Let's take a closer look here about what I mean inside the zkVM. This is basically the picture that I showed you before, but zoomed in. And we have an object called an executor and approver inside the zkVM. And there's this notion of an execution trace. And in order to generate a proof for the correct execution, we need to sort of do something with this execution trace. So just to sort of highlight the public outputs of your proof here can be kind of arbitrary parts of the execution trace. So a few months ago, we introduced this feature called continuations, and I want to sort of unpack the connection between continuations and recursion. Before we had continuations, we were able to generate proofs at max of 16 million execution cycles, 16 million, it's not exactly 16 million RISC-V instructions. There's sort of, not every RISC-V instruction is exactly one zkVM cycle, but roughly speaking, you can think of this as 16 million machine instructions. After continuations, we don't really have a limit here anymore. We can generate proofs for arbitrarily large RISC-V executions. So far, I think the biggest that we've done is something like 10 billion. And our napkin math for our theoretical max here is something like 100 trillion. We'll see whether that theoretical max is, I don't think it's going to happen anytime soon. But so I want to sort of connect the dots here of how this comes back to recursion. So this is the picture that I showed you before. And what we do at RISC Zero is we split our execution trace into a bunch of segments. And we prove each of those segments in parallel. So rather than proving SNARK for 1 billion cycles, we typically are splitting our execution trace into sections that are each 1 million cycles long. So if you're looking at a 1 billion cycle computation, I guess that's 1,000 segments each or 1,000 segments each 1 million cycles long. So we get a receipt for each of those segments, a proof for each of those segments. And then we feed this into recursion in order to compress this into a single proof. So in some sense, this is still using recursion for proof aggregation, but I want to kind of call it out as separate because it's proof aggregation for the purpose of incrementally verifiable computation. So in particular, this is not the slide I expected. Oh, yes, OK. So we get to discuss this question of how should we make the proofs. And I want to just call out that we need to be more specific about which proofs are we talking about making here. We need to make proofs for RISC-V execution. We need to make proofs to aggregate those RISC-V proofs for IVC purposes. And we need to make proofs to aggregate the full RISC-V proofs. In our system, we're using a RISC-V circuit for this first part, and we're using a recursion circuit for the second part. But we might decide at some point to switch one of those to something other than a recursion circuit. So for example, it might be plausible to use a sort of folding-based approach for the second item on this list, but still decide to use a FRI-based approach for the third item on this list. So we're using SNARKs for all of these. And the problem is that SNARKs are too big for use on chain. The proof size for SNARKs in our system is about 250 kilobytes. The gas costs are too large to make it feasible to verify on chain. I don't even think I think the call data limits are a barrier here. So we add one more proof to our stack, which is this kind of SNARK wrapper. So this was the picture I showed you a second ago. We have one more circuit in our system, and this spits out a little teeny tiny proof. So this was the pattern that I showed you in the first slide. Again, these are FRI-based proofs here, FRI-based proofs here, and in our case, Groth16 here, and the other systems, KZG. So let's expand that a little bit. This is that picture that I just showed you. This is one full proof of a RISC-V execution, including segmenting and recursion. Here's another one, here's another one, and here's another one. And then we could aggregate all of those as we did before using a recursion circuit. And finally, at the end here, we're going to only worry about the Groth16 wrapper at the very last step. So in the picture I showed you before, there was a Groth16 step after these steps. But in the full, like, with proof amortization, with the full proof aggregation, this is the architecture that we're working with. And if you look across zkEVM, like the Polygon zkEVM has a very similar diagram on the website, and I think Boojum does as well. OK, so our approach is Starks for the zkVM circuit, Starks for the recursion circuit, and then we're using a Groth16 SNARK to make the proof small. That's ours, Polygons, and Boojum's. So now we get to the interesting part. Is this a design that is good? Is this a design that we should stick with? Our thesis for now is yes. And we remain open to sort of exploring other options as they come in front of us. At this point, we don't see an immediate cause to switch. But I want to just sort of outline some of the considerations that would drive these sorts of decisions. So the one that, or I guess the two that are really kind of obvious is proof size and proving time. We definitely want proofs to be fast, and we would like the final proof, at least, if we want to put it on chain, to be small. And when you see new papers, it's easy to get excited about, look, this paper is clearly like we should switch to this because the proving time is better. But it turns out that there's actually quite a lot more complexity in choosing a proof system than just proving time and proof size. We also might be interested in the hardware requirements. We are interested in whether this is something that you can run on a consumer machine or whether you need a sort of giant, epic supercomputer to run. We are interested in how parallelizable this is. The difference between a system that runs fast on a single machine versus a system that is easy to horizontally scale to a cluster of 100 or 1,000 machines, it's not necessarily super obvious. It might be the case that one system is optimized if you're not trying to horizontally scale, and another is preferable if you are trying to horizontally scale. We're also interested in whether this could be decentralized. Is it possible to ask a bunch of nodes to each participate in a collaborative proving process? And we're also interested in security and auditability and privacy, and I could expand this list further. But I just sort of want to highlight that there's a number of axes that we need to consider in comparing these proof systems. And what I want to do for the remainder of the talk is sort of outline some of the details. I'm going to focus on these top 5, and we'll discuss a little bit of how this looks in the emergent pattern that I just described, and discuss a little bit of how some of the alternatives may offer some challenges in terms of some of these axes. So let's first just talk proof size. This is, I think, the simplest one. The Starks that we're using are about 250 kilobytes. The SNARKs that we're using are under 100 bytes. So it's a pretty substantial difference between the size of a Stark proof versus the size of a KZG or Groth16-based proof. The prover time here, I'm giving these numbers here. This is 11 seconds for a segment proof. So this is for proving one segment of 1 million cycles. Takes 11 seconds on a MacBook M2. This is actually an M2 Pro, I realized after I made the slides. The recursion is faster. And the Groth16 is actually kind of a substantial portion of the proving time here. So this description here is worth unpacking a little bit here. If you're running this on a single machine, you're going to have to do 6 of these for the example that I have shown here. But, I'll get to that a little bit later. So for right now, let's just I'll just highlight, if you're running this on a single machine, you do need to do that once for each segment. There's a sort of foreshadowing, I guess, of discussion of parallelization here. Can we run these on regular computers? Can we run these on your laptop? This is a sort of real kind of consideration. If you look at the details for a lot of proof systems and you're like, oh, what's the hardware that you're running this on? There's systems that are requiring over 100 gigabytes of RAM in order to be able to run it, which is okay, cool. If you have a supercomputer or you want to pay for one, great. But it's nice to be able to generate this on a standard laptop. This 12 gigabyte number here is based on the size of these segments. So right now our default segment size is 1 million cycles, which means that in order to generate a proof, we need to do a number theoretic transform, or FFT, on 1 million cycles. And the hardware requirements here translates to about 12 gigabytes. We can tune this down. If we just sort of set the segment size to something smaller, then the hardware requirements drop accordingly. So this is like a configurable setting. If you have a desire to be able to run this on a lower power machine, we can sort of dial that back a little bit. The Groth16 circuit here, we have substantially less control over tuning, but fortunately it can also run on a consumer laptop. Okay, let's get into the more interesting stuff. How well can we parallelize these systems, and how well can we decentralize these systems? This initial production of the execution trace is happening on a single machine. This is our current kind of a big effort is, can we easily parallelize this initial construction of the execution trace? So far, it's just running on a single machine. These ones, though, the segment proofs here, of which in the example I have here, this is like a 6 million instruction proof. So there's 6 of these. We can delegate these to a cluster. So if we have 6 machines on our cluster, we can ask each of them to prove one of these segments and send back the result. And similarly, for this kind of proof aggregation part, we can similarly delegate this to a number of machines. And the SNARK compression at the end is happening on a single machine. So interestingly, the question of how difficult it is to parallelize depends a little bit on whether you're parallelizing it within a cluster that you are controlling yourself and have high bandwidth between the different machines, versus if I'm sending something to somebody else that's not inside my data center, and I'm saying, hey, I want you to prove this for me. So the question of like communication complexity is important when we start looking at questions of decentralization. So I want to discuss, like, if I am asking, I know I want all of this work to get done, and I have some collection of machines that are happy to help me with this work, and I want to say, hey, can you do this part, can you do this part, can you do this part, and then everybody just send me the results and we'll move forward. I want to just discuss, like, how much information do we need to actually send back and forth in order to decentralize such a parallelized system? So what actually needs to get specified in order to do each of these parts? This execution, we need to specify a binary file, and we need to specify some inputs to that binary file. That's what the prover needs to receive. And then the prover is going to send back some collection of segments. Each of these segments, this is like a pre-proven segment. This is just a description of the portion of the execution trace, is about 50 megabytes. So that means that in order to assign this segment proving to some node in my decentralized network, I need that node to receive 50 megabytes from somewhere. And, oh, sorry. Yeah. Oh, yes, this is correct. The executor needs to receive the binary file and inputs, and the executor is going to return 50 megabytes per segment. Then we're going to send each prover one segment. They're going to receive 50 megabytes, and they're going to send back a SNARK proof. So they're going to send back 250 kilobytes. For the recursion, if I'm trying to combine 2 proofs into one, the person doing the combining needs to receive 2 SNARK proofs, and we'll send back 1 SNARK proof. So they'll receive half a megabyte and send back 1/4 megabyte. And then finally, this Groth16 circuit will need to receive 250 kilobytes, and we'll send back just 100 bytes. So one question that often comes up when we're discussing these sorts of proof systems is, well, what about folding? Why not use folding? And when I think about the sort of feasibility of transitioning from the current architecture that we're using to like a folding-based architecture, the main challenge that I see is the question of like, how do we horizontally scale a folding-based system? Intuitively, I think running a folding-based system on a single machine may be a faster approach than what we're doing here. But if I want to delegate the work to some individual node in a folding-based system, rather than sending them a SNARK, I need to send them a witness, which means rather than sending 250 kilobytes or 500 kilobytes, I need to send them some like tens of gigabytes. And then they fold it, and they need to send back some tens of gigabytes. And so the practicality of like the communication complexity of a folding-based system in a horizontally scaled system feels like a major challenge that so far I haven't seen a whole lot of discussion around. So as I'm sort of thinking about the question of, do we want to stick with this proof system, folding seems very exciting as something to switch to. But until we have some more clarity about like how do we handle this communication complexity of a horizontally scaled folding-based system, it feels like a bit of a, I don't know if I should say non-starter, but at least a challenge that we need some answers for. So that's what I have prepared. I'm happy to take questions about any of these details. I have, yeah.
Thank you for the talk. In the numbers you gave there, so you were describing essentially, yeah, passing around proofs between things to then do recursion. Presumably, you also have to pass around the inputs to those proofs, in particular for ensuring that like the individual segments connect together in the correct order.
Good point.
Is that a rounding error in these numbers, or does that?
Yeah, let's unpack that a little bit. So where should I look? I guess it's here.
Like, is it hidden in the tilde, or is it something that also needs to be taken into account?
Yeah, no, good question. So for this part, we don't need to pass around those sorts of like making sure that it's just for this part that you're really, I think, referring to. Is that correct?
Well, I presume also for then, it depends. I don't know for, because again, it came back to you described it as having, you're using one circuit for two steps. Both for compressing proofs together and for combining the different segments of execution trace. And one of those requires ensuring that the segments are correctly ordered and connected, and the other one doesn't.
Yeah, okay, yes. So the call out here is in order to make sure that when I aggregate these proofs, I actually have a valid proof of the execution trace, I need to make sure that the segments are appropriately sequential. I need to make sure that the end state of segment 1 lines up with the beginning state of segment 2. Which I think it's like a tiny snapshot here. We need to provide we provide the full memory state for the initial, and we provide a hash of the memory state for the end. So the full memory state initially, we're looking at like 270 columns, each of which is a 32-bit finite field element, so it's not a huge number, and the hash at the end is tiny. So,
cool. So
yeah, I think it's built into the tilde.
Cool, thanks.